We're going to learn how to use the comparison tests and the ratio tests to determine whether a series, an infinite sum, converges or diverges. So this is a bit of a long demo and a short activity. I'm sorry, but I want to, let me just sort of overview what we're doing. So we've been talking about series for a couple of classes, and we have covered the first 1, 2, 3, 4 tests in this chart, which is the first page of your packet. Today we're going to do the next 3 together, and I could make the demo really fast if I just was like, this is the test, here's how you use it. But we're going to kind of, I'm going to try to spend some time developing like why the tests are what they are and why they work. So it takes a little bit of a time investment to really understand why the tests work, but it helps to remember in the long run if you understand the whys behind the tests. Okay, so the first test for convergence today is the direct comparison test. So this test is very similar to the comparison test for integrals that we used earlier in the term. It was on your second test. So you can compare them later to see the similarities. We're going to determine whether or not each series converges by comparing to a series whose convergence we know. And it's going to be the same concept as the integral comparison test. If your series is larger than a divergent series, that means it's larger than something infinite. It must also diverge. If your series is smaller than something convergent, it's smaller than something finite, it must also converge. So the p-series test, 1 over n to the p, remember it converges for p is bigger than 1, it diverges for p is less than or equal to 1. That was something we concluded last class. It's also convergent for 1 over an exponential. Right? Okay, so my sum from n equals 1 to infinity of 1 over 3 to the n plus n, I have a couple of choices to compare to. I could compare to 1 over 3 to the n, or I could compare to 1 over n. So let's look at 1 over 3 to the n plus n, and I'm going to compare it to, say, 1 over n. Less than or greater than? The denominator is bigger. So this denominator is n. This denominator is n plus some positive amount, right? So the denominator on the left here is bigger, which means that this fraction is smaller. So this is less than. Okay. Or I have another easy comparison I could make. I could do 1 over 3 to the n plus n, and I could compare that to 1 over 3 to the n. 3 to the n plus some positive value is larger than 3 to the n. So 1 over a larger value is smaller. Okay, one of these comparisons is helpful because I know the convergence and divergence behavior of 1 over n and 1 over 3 to the n. So the infinite sum of 1 over n, converge or diverge? Maybe check the p-series test up here. Diverges, yeah. P less than or equal to 1. My p is a 1 in this case, so this diverges. So being smaller than something infinite tells you nothing, right? It could also be infinite and it could be finite. So this comparison is unhelpful. Being less than something divergent is unhelpful. But 1 over 3 to the n, this converges. And so my sum is smaller than something finite. Okay, so this tells me that my sum is also going to converge because it's smaller than a convergent sum. Okay, so because this is true, I'm just going to write out a final sentence to sort of conclude the problem here. So because 1 over 3 to the n plus n is smaller than 1 over 3 to the n, the sum from n equals 1 to infinity of 1 over 3 to the n plus n is less than the sum from n equals 1 to infinity of 1 over 3 to the n, which converges. Right? So my sum is smaller than a convergent sum, so it must also converge. Thus, the sum from n equals 1 to infinity of 1 over 3 to the n plus n also converges. All right. Very similar to the integral comparison test that we learned a couple weeks ago. Okay, one more, same idea. I have an infinite series, and I want to know whether it converges or diverges. I'm going to compare it to some series whose convergence, divergence behavior I already know. So 1 over 3 to the n plus 1 over n. I'm going to do the same comparisons, right? If I compare this to 1 over n, and then I'm going to also compare it to 1 over 3 to the n, one of them will be useful, one of them won't. Okay. 1 over n equals 1 over n, right? 1 over n and 1 over n are equal. On the left here, I've added to 1 over n some positive amount, right? Because n is positive, so 1 over 3 to the n is some positive amount. So which side is bigger? The left. Yeah. 1 over n plus some more is bigger than 1 over n. So that's bigger. And then over here, the inequality is the same direction, right? Now, 1 over 3 to the n plus some positive amount is going to be bigger than 1 over 3 to the n. One of these is helpful because of the convergence divergence behavior of 1 over n and 1 over 3 to the n. 1 over n diverges, the sum diverges, and 1 over 3 to the n, the sum converges. So being larger than something that converges is not helpful, right? You could be larger than some finite number and still be finite, or be infinite. So this is an unhelpful comparison. But this one, because this sum diverges and this sum is bigger than it, it has to also be infinite. So I'll write a sentence about why this tells me that the sum converges. Okay, so I'm going to say, since 1 over 3 to the n plus 1 over n is greater than 1 over n, this sum, 1 over 3 to the n plus 1 over n, is larger than the sum of 1 over n. And then I'll say, since the sum, the infinite sum of 1 over n diverges, so must the infinite sum of 1 over 3 to the n plus 1 over n. All right, if I try to use the comparison test on this series, I have n to the 1.5 over 2n squared plus n plus 1. So a series that it makes sense to compare to would be 1 over n to the 0.5. Why is that the comparison? Why did I choose it? Yeah. Yeah, you look at the leading terms. N over 1.5 over n squared. N to the 1.5 over n squared. That's 1 over n to the 0.5. And I'm ignoring the 2. It's not that the 2 is not important. It's just that I want to compare to a p series, right? I want to compare to something whose convergence divergence behavior I know for sure. So 1 over n to the 0.5, I know what it does because that's a p series. P is less than 1, so it diverges. So I would like to compare to 1 over n to the 0.5, but when I do my comparison, so I'm going to have n to the 1.5 over 2n squared plus n plus 1, and I want to compare that in terms of size to n over 1.5, which is the same thing as n to the 1.5 over n squared. And I wrote it in this format because now the numerators are the same, and I can just compare the denominators. So 2n squared plus n plus 1 is larger than n squared, right? You're doubling it, you're adding some more. So this denominator is larger, which means the fraction is smaller. And this is an unhelpful comparison because this diverges, right? N to the 1 over n to the 0.5 diverges. And being smaller than something divergent is an unhelpful comparison. We have no idea whether our thing is finite or infinite. So this is unhelpful. So that's why the comparison test doesn't apply, right? It tells us nothing helpful. So instead, we're going to use something called the limit comparison test. So this is just a different way of comparing the same two series. I'm going to compare this series to this series, but instead of comparing term by term, I'm going to compare the ratios of the terms and see what happens. Okay, so I'm going to do it over here. I'm going to take the limit as n goes to infinity of n to the 1.5 over 2n squared plus n plus 1. And I'm going to take the ratio of that, the terms of that series to the terms of my comparison series, 1 over n to the 0.5. So this is the limit as n goes to infinity. Dividing a fraction by a fraction, I'm going to flip and multiply. So I have n to the 1.5 over 2n squared plus n plus 1 times n to the 0.5 over 1. Okay, so now when you multiply fractions, you just multiply the tops, you multiply the bottoms. N to the 1.5 times n to the half. Multiplying like bases, you would add the exponents. That becomes an n squared on top. And my denominator is 2n squared plus n plus 1. And then this is the limit as n goes to infinity of a rational function. The degree of the numerator and the denominator are the same, which means the limit is the ratio of the leading coefficients, 1 over 2. Okay, so 1/2, it's not 0, and it's not, it's finite, and it's not 0. That is what the limit comparison test tells us to look for. It says if you compare the terms of two infinite sums and you get a limit that is finite and not 0, then the two sums have the same behavior. They either both converge or they both diverge. Okay. So 1/2 is not 0 and finite, which means that the sum I was interested in has the same behavior as 1 over n to the 0.5, and we know that thing diverges. So my final sentence here is going to be the sum of n to the 1.5 over 2n squared plus n plus 1 converges just as the p series converges, 1 over n to the 0.5. Okay, because the limit was non-zero and finite, both of those sums have the same behavior. And I know the behavior of 1 over n to the 0.5 is divergent. Sorry. Okay, so that feels, I could just move on and be like, that's the test, right? It has to be non-zero and finite. But I just want to like dig in a little bit and say, like, why is that what it has to be? Why does non-zero and finite mean that they have the same behavior? So let's compare two things that we know have different behavior. 1 over 5n, we know diverges, and 1 over n squared, we know converges. So if I apply the limit comparison test, I should either get infinity as my limit or 0 as my limit. So let's just do a quick check. The limit as n goes to infinity of 1 over 5n compared to 1 over n squared. So this is the limit as n goes to infinity of 1 over 5n times n squared over 1, which is the limit as n goes to infinity of n over 5. And what is that limit? Infinity. As n goes to infinity, n over 5 will also go to infinity. So this actually means that we can't conclude anything, right? The limit comparison test says that if that limit is finite and non-zero, then both sums do the same thing. It doesn't say what happens if the limit is infinity or 0. So we have to say no conclusion here. We happen to know that these have differing behavior. But if we didn't, we would have to say like, oh, we'll have to do another test. We can't tell from this test. All right, and then one more, I'm going to compare them, but I'm just going to do the division in the opposite order. The limit as n goes to infinity. What if I do 1 over n squared compared to 1 over 5n? So this would be the limit as n goes to infinity of 1 over n squared times 5n over 1. The limit as n goes to infinity, my n's cancel, and I get 5 over n. What does that go to as n goes to infinity? 0. So this one came out infinite, this one came out 0. So that's what we would assume would happen for two series that have different behaviors, right? That we would get infinity or 0. So again, that tells us nothing. We happen to know that they have different behaviors, which is why we got infinity and 0. Okay, let's try to use the limit comparison test for the infinite sum of n to the 5th over 3 to the n. What does your intuition say about the convergence divergence of this? What do you think? Converge or diverge? You think it converges? That's a good thought, right? Because in terms of the numerator or the denominator dominating, an exponential is always going to grow faster than a polynomial. So eventually 3 to the n is going to be so much bigger than n to the 5th that that's going to be like the series 1 over 3 to the n. So that's what I'm going to compare it to, right? Because n to the 5th is going to be so much smaller than 3 to the n that I think this series is going to behave like 1 over 3 to the n. Okay, because 3 to the n is going to win. It's much, much bigger than n to the 5th if you're plugging in like a quadrillion, right? Something really big. So I'm going to do the limit comparison test and see what happens. The limit as n goes to infinity of n to the 5th over 3 to the n divided by my comparison series 1 over 3 to the n. And I know that this converges. Okay, so this is the limit as n goes to infinity of n to the fifth over 3 to the n times 3 to the n over 1. Cancel, cancel. This is the limit as n goes to infinity of n to the fifth. What is that limit? Infinity, yeah. That means that I cannot conclude that the two series have the same behavior, right? The limit comparison test says that my limit has to be finite and non-zero, but this limit is infinite. So I can draw no conclusion here. That doesn't mean that they don't have the same behavior. It just means that we still don't know. We're going to have to do another test. So my next test is the ratio test. So it says that for a series, n goes to 1 to infinity of a sub n, if you look at the ratio of successive terms, the n plus first term divided by the nth term, take the limit as n goes to infinity, that comes out to some limit L, okay? If L is less than 1, the series converges. If it's bigger than 1, the series diverges. And if it equals 1, the test is inconclusive and we have to do a different test. All right, so why does this work? What test that we already know looks at the ratio of successive terms? One term divided by the one before it. The geometric series test. And if that ratio was between -1 and 1, then it was a geometric series that converged. If it's bigger than 1, it diverges. So this is basically an extension of the geometric series test. It says that if you go really far out in the list, eventually the series looks geometric. And if that constant multiplier is less than 1, it converges. So this is, this says that the series is basically geometric when n is big. And your conclusions are the same as the geometric series test. If that limit is smaller than 1, converges, bigger than 1, diverges, equals 1, do a different test. Okay, so let's look at this same series that we just failed to draw a conclusion about using the limit comparison test. We're going to try with the ratio test. So the ratio test says take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. So the n plus first term divided by the nth term. Okay, so the n plus first term means replace your n's with n plus 1's. So this is going to be n plus 1 to the fifth over 3 to the n plus 1. That's a sub n plus 1. And a sub n is just the term that was written in the series. So n to the fifth over 3 to the n. So this is the limit as n goes to infinity of n plus 1 to the fifth over 3 to the n plus 1. And instead of dividing by this fraction, I'm going to multiply by its reciprocal. So multiplied by 3 to the n over n to the fifth. So now I'm going to try to simplify this. So 3 to the n over 3 to the n plus 1. Those are like bases, so I can subtract the exponents. N plus 1 minus n is 1. Where should I put my 3 to the first, numerator or denominator? Denominator, because there are more 3's in the denominator than the numerator. So I'm going to have some canceling here. 3 to the n is going to cancel with this, and I'm going to have 3 to the first left over. And then n plus 1 to the fifth. I could multiply it all out. That's n plus 1 times n plus 1 times n plus 1 times n plus 1 times n plus 1. What is the highest power of n going to be if I multiply this all out? Yeah, 5. This will be n to the fifth. And then there's going to be some lower order terms. So let me write this. Goes to infinity. My numerator is going to be n to the fifth plus a bunch of other stuff. Maybe some n to the fourth, some n cubes. I don't really care what they are, so I'm just going to write stuff there. And then my denominator has a 3 n to the fifth. So now I'm taking the limit as n goes to infinity of a rational function. The degree of the numerator and the denominator are the same, which means that the limit is the ratio of the leading coefficients. So it's going to be 1 over 3. Limit is 1 over 3. What does the ratio test tell me if my limit is 1/3? It converges. The limit is less than 1. That means my sum converges. So I should write since the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1, the sum, what was my sum? N to the fifth over 3 to the n converges. So our intuition was right that this thing would converge. It just took us a while to prove it. We had to find a test that would give us that result. Okay, another one. We're going to do the ratio test on this one too. So I'm going to take the limit as n goes to infinity, big absolute value. The n plus first term means just make your n's n plus 1s. So this is 4 to the n plus 1 over n plus 1 factorial divided by 4 to the n over n factorial. Okay, so then I'm going to flip and multiply 4 to the n plus 1 over n plus 1 factorial times n factorial over 4 to the n. Okay, so my 4 to the n plus 1 over 4 to the n, you subtract the exponents, you get 4 to the first, and it's going to live in the numerator. So I'm going to have a 4 in the numerator. And then n factorial over n plus 1 factorial. Maybe I'll write out some terms to see what happens. N factorial is n times n minus 1 times n minus 2 down to 2 times 1. And then n plus 1 factorial, that's n plus 1 times n minus 1 times 2 times 1. Okay, so cancel common terms. These all cancel. And I'm left with 4 over n plus 1. All right, what is the limit of, as n goes to infinity, of 4 over n plus 1? Mm-hmm. 0. Denominator is going to get really, really big. Fraction gets really, really small. Okay, so 0. Let's see, does that fit any of our categories here? It is less than 1, so it converges. Since L equals 0, which is less than 1, the sum of 4 to the n over n factorial, is that the right order? Yeah, converges. Say by the ratio test. All right, last one. I'm going to do the ratio test on this polynomial. So I take the limit as n goes to infinity of n plus 1. I'm replacing all the n's with n plus 1's. 2 times n plus 1 squared plus n plus 1 plus 1. And I want to divide that by just the plain old n's. N over 2n squared plus n plus 1. And that's all in absolute value. Okay, so now I'm going to flip and multiply. I have n plus 1 over 2 times n plus 1 squared plus n plus 1 plus 1 times 2n squared plus n plus 1 over n. Okay, so just imagine, remember when you multiply fractions, you multiply the tops, you multiply the bottoms. So I've got an n plus 1 times 2n squared plus 1. What's the leading term going to be after you multiply those together? You don't have to multiply every single thing together to figure out what the leading term will be. 2n cubed, yeah. When you distribute this n to the 2n squared, you get 2n cubed. And that's going to be the highest power of n that appears anywhere in your multiplication. So my numerator is going to be 2n cubed plus some stuff. Smaller powers of n. Okay, my denominator, if I have all this multiplied by n, what will my leading term be when I multiply this all out? Again, 2n cubed, yeah. So this is going to give me a 2n squared right here. And when I multiply by this n, I'm going to get a 2n cubed. So I don't even care what the rest of the stuff is. There's some lower order stuff, some smaller powers of x, smaller powers of n. But I don't need to know what those are in order to take the limit, because the limit only depends on the leading terms. So my degrees are the same. They're both cubics. So I take the ratio of leading coefficients. I get 2 over 2, which is 1. So what does the ratio test tell me when the limit is 1? Nothing. No conclusion. So I would have to turn to a different test. See if I can use a different test. What would you use if you had to decide if this sum converged or diverged? You think it converges? Yeah, it does. Wait, no, it does not. No. No, it does not converge. It diverges. And what test would you use to try to prove that? I think I would do the direct comparison test. I would compare to 1 over n. Right, just look at the ratio of the leading terms. N over 2n squared would be 1 over 2n compared to 1 over n. It should have the same behavior. So either do a direct comparison or the limit comparison test. Okay, but the moral of the story for the ratio test is it works really well if a series involves a quotient that has factorials in it or exponentials and powers, right? But if it's only powers, if it's just a quotient of polynomials, like the example we just did, don't bother with the ratio tests. The limit will always be the dreaded 1, and you won't be able to draw any conclusion. It takes some experience to recognize when to use which test. Definitely use the tests for convergence of infinite series sheet that is the first page of your packet, this one, right? It names the test. It says, used for what kind of series. It tells you the conclusions you can draw, and when it tells you nothing. It's really helpful. Use it while you're working on homework, class activities, bring it with you to the test, etc. But even with that, expect to make some false starts, right? You'll try a test, it'll tell you nothing, you'll have to do a different test.